On air now. Yes. Ah, I see now. Yeah. Okay. Thank you very much for the invitation. It's a great pleasure for me, honor to be here. I'm very much pleased. And thank you for giving me an opportunity to give a talk here. Well, the title of the talk is here. As you can see, metric approximation of set-valued functions, specifically of bounded variation. What metric does mean, I will explain it. This is joint work with three ladies from Tel Aviv, Nira Dyn, Farkhi, and Elena Mokhov. Elena is the joint former PhD student. It was maybe 10 years ago that she was a PhD student. Okay, so what is this about? We want to approximate set-valued functions. It means that the values of functions are sets. And I'm specifically interested in, this is our step. We consider functions such that their values are compact, non-empty sets in RD. So the setup is we are working in the space RD and the values are compact. A very particular important case is when the values are convex set. So I will denote the set of convex compact sets by this symbol, compact of RD, and we consider functions defined, say, on a compact interval AB for one variable. Well, let's restrict our attention to one variable, and the images are compact sets in RD. Such functions are called cell-values functions, and I will abbreviate it many times, but these SVF, set-valued functions. And in particular, what we are trying to do here, we are trying to work with classical approximation operators and see how we can extend them so that they also can be somehow adopted to this setup. I must warn you that it's not so obvious that it can look like that these functions with values of sets, it's not even a linear space. There are no natural operations, so you cannot just say what the sum of such functions is. This is all non-trivial, because how are you going to add two sets? Because there are different ways, different definitions how to do it, but everything what goes on is very much dependent on it, but definitely there is no linearity, so it's not even a linear space. So it's something really different, and maybe I say at this point that my talk is concepted in the following way. I would say the most part of the talk is the introduction, so I'm going to tell you the most part of the talk just to tell you about the setup, explain what is specifically our interest is working with compact, not necessarily convex functions, to explain you why the known methods are not working in this setup, why there is a need for other approaches, and then somewhere on the end shortly show you where we are now, and it's still the beginning of the work. So there are more, I would say, more plans than results at the moment. Okay, approximations of functions specifically with convex images is not a totally new thing. There are works on it, there are names. This is just some selection here. An American mathematician, I'm not sure how to pronounce this name, Vitale.
No problem.
Vitale, yeah, I would say also Vitale. Yeah. Okay, I have no idea. So there is a paper where he adopted the classical Bernstein operator to the set-valued functions. I will explain what he did and explain his results later. Then Nira Dyn, Farkhi, and a number of students studying since the 80s, so they do it long time. They have different approaches, really very different methods here. Large literature on this subject. Mureshan published a survey 2010, where he in particular also quoted Nira and Elsa and Alona. There is also a paper from Ukraine / United States, Vladislav Babenko, Vera Babenko, and Maria Polishchuk, recent paper where they did some kind of trigonometric approximation, well, maybe I shouldn't go into much detail. So what is a trigonometric polynomial for set-valued functions? Even this is not known. So they consider the question of best approximation by some kind of functions which are a convolution of a real valued usual trigonometric polynomial with a given set-valued function. So these are the trigonometric polynomials, and the integral in the convolution is the Aumann integral. I will also explain what it is. So the point is, all these methods, many methods, they're all convex. In the sense, the usual problem here is convexification. This means that if you build something out of it, I will show linear combinations and integrals, you will see really what goes on there, that the result is convex, even if the original function was not. And that's why these all methods are quite okay for approximation of functions whose images were convex. But of course, there are situations in life where the functions are not convex. And for that, these methods are not useful anymore. All these kind of problems here, apart from being theoretically interesting and having applications in different areas of mathematics where people work with set-value functions, like, for example, optimization and mathematical economics, and also differential inclusions in control theory. This is what Elsa was doing here. So that the aim is in the control theory that, so to say, the result, your point achieves the set, so that the condition is an inclusion, not f of x is equal to something, but f of x is element of a certain set. Yeah. So these things, but it has also applications in practical life, in engineering, especially in medical imaging. So just imagine a set-valued function. Oops, what's going on?
No, it's good. It's okay.
So it's automatic. Okay. Got totally scared. So let's imagine a medical imaging. Let's imagine, let's say, whole bones here. Yes, so here or here we have two bones. They are complicated. So I don't know. I'm not good in. So we have something like this here. And now a device makes measurements at certain levels, make cross sections. So what we have on the end, we have some set of cross sections of a three-dimensional object in a certain steps. And the practical problem is to recover the three-dimensional object based on the set of two-dimensional cross sections. So you don't know what is in between. You need to feel it somehow. Yeah? This is, for example, one of the practical setups, and there are things also in engineering going on about it. And it's clear that in many practical applications, the images are not convex. The objects are not convex. Like here, for example, it's not even connected. Yeah. So this is what is going on to happen. How do I return? Oh, fantastic. Okay. Pioneering work on approximation of functions whose images are not necessarily convex. Here, Bernstein, and what he did, he constructed exactly for the problem where I discussed. So values of functions are given a certain mesh, and he constructed an interpolant, namely a piecewise linear interpolant, or even interpolation. I wrote here approximation, actually interpolation, and his idea is basically the same what we will be doing later. So like, so to say, how to say? So it's also metric, what we now call metric interpolation, and I will explain what it is, and then I will maybe mention what he did. Okay, so there are some works known, but for the non-convex case here, just not many ideas, just one particular method, and it seems that there is a big need in methods for approximating non-convex functions or functions with non-convex images. A couple of boring slides with notations. We work in RD, and we consider norm in RD. Doesn't matter which. I remind you that all norms are equivalent. That's why the constructions will be maybe the constants a little bit depending on it, but basically it's all the same. And the distance rule between the points in RD is just the normal difference. And how do we measure the distance between two sets? This is also known construction, the Hausdor distance, which is defined like this. My sets are all compact, that's why it's always minimum and maximum, not supremum and infimum. So for one set and a given point, this is the usual definition, the distance between the point and the set. Yeah, so we just look for the point which is the closest and the Hausdorff distance that we maximize all over the points. Yes, it's a known construction. Both spaces of the compact sets and also the space of compact convex sets are complete metric spaces with respect to the Hausdorff metric. Okay, now for a given set B and the point A, we denote by pi sub B of A the set of all projections. This means these are the points that realize the distance. I don't know how, this is again, I don't know how well you are familiar with all this stuff. So let's say here is my point, and let's say here is the set. I'm working with the usual Euclidean distance here, and this must be a part of a ring. So then where are the projections? They all lay here at the same distance. And the set of projections will be this arc. Yeah? And for two sets now we do opposite, other way around also. And 2 points A of the set A and B of the set B are called metric pair if one of them is a projection of the other one. And these are basically the pairs that play a role when we calculate the Hausdorff distance. The Hausdorff distance is the maximum of distances between all metric pairs. And it is a very important concept, so I don't take too many points from this set. I just really consider only metric pairs. And this is also was the idea of SVFs that in his linear interpolation, what we did, let's say we interpolate between two values, that he connected metric pairs to each other by just linear pieces, and this is his linear interpolant. So as I told you, the idea working with metric pairs, and now we will also work with metric pairs all the time, but go much, much further. Yeah, do also other things. Okay, this is also a small notation. The distance of a set A to the point 0 will be denoted like norm, and this usually in this context is called the norm of the set because it's not a norm. But that's why I put it in the quotation mark. So this is not a norm. There is also no structure of linear space. Okay, another two objects, another two notions that we use here for a sequence of sets. The upper Kuratowski limit is the set of all, I won't read it here, but just say the set of all limits of convergence subsequences. Opposite to it is the lower Kuratowski limit is the set of all limits of convergence sequences. I think it's easier I explain it by an example, what it is. I take a very, very trivial example, two sets which will be repeating all the time. So one set like this, one like this, this, and so on. So this is my sequence. Yeah, and so on and so on. So like first first, the second, the first, the second. So let's understand what the upper Kuratowski limit and the lower Kuratowski limit is. The upper Kuratowski limit is all limits of all subsequences. So this means I can always take a subsequence which takes only the negative, the odd numbers, and then I will get this entire set. But then also I can take subsequences that only have their even numbers, and then I get also this. But then it's clear that I cannot get more than the two sets together. So in this sense, the upper Kuratowski limit is this bigger set, but the lower Kuratowski limit are the limits of sequences that really go through all sets. And it's clear that in this case it can be only this. And then you see also the problem, the lower Kuratowski limit must not exist. Yeah, also in this example, if I take these my two sets and pull them out of each other, then the lower Kuratowski limit is empty. But the upper Kuratowski limit exists always under some slight conditions that are fulfilled. In our case, for example, we say that our sequence is bounded, and then by the compactness argument, you will have always convergent subsequences. So it's not empty. I didn't put it on the slide, but the set, if the lower and the upper limit both exist and coincide, that the sequence is convergent. So this is Kuratowski convergence. In the metric, in the compact metric space, the Kuratowski convergence coincides with Hausdor convergence. So this is basically the way to work with the Hausdor convergence. One way to work with Hausdor convergence, considering the Kuratowski upper and lower limit. The usual way to define a linear combination of sets is the Minkowski linear combination. I think everybody saw this in life, so this is really absolutely standard thing. For their sets A0, A2, and so on, An, we take all possible. I want to define this linear combination. Yeah? Lambda I are some real numbers. So I take all possible linear combinations where the point AI is coming from the set AI. So this is the Minkowski linear combination everybody uses. But what is the problem with this in our context? The convexification. So let's consider the following simple example. We consider the set A, so all AE are equal to A, and this is the set containing only 2 points, 0 and 1. And now I want to find an average of n copies of this. 1 over n, right, from 1 to n A. So we would expect if I take an average of the same set, then the result must be the set itself. Yeah? This is not how it goes. Why? If I take n copies, so now this is my set, yeah? So I take n copies and sum up. Yeah? So the values here are 0 and 1. So from each set I take 0 or 1. So on the end I have all possible numbers k here. Yeah? If I take k once and n minus k 0, then the sum is k. Then I divide it by n. And so we see that the sum is the set 1. So in addition to the points y, 1 and 0, we also obtain many points in between. And when now one goes to infinity, then we obtain the entire interval 0 to 1. So the convex hull of the set. This is exactly what we don't want to have. Because we really want to keep the holes, we want to keep the structure of being non-convex. And what is the problem? We take too many linear combinations in the Minkowski linear combination. So the idea from the idea of Nira as Alena was, okay, we don't take all possible linear combination in the Minkowski linear combination, but we just only take always metric pairs. So this, maybe I show immediately the second definition. So we call it the metric linear combination. Metric is come from this term metric pairs. So we consider here linear combinations, but not all possible choices of A, but only for the following choice. If I have a set of sets, collection of sets, A0, A1, and so on, AN, a metric chain is a sequence of points, one point from each set, such that each neighboring points are metric pairs. And then we consider only linear, so we call each such sequence metric chain, and we consider in the metric linear combination only points from metric chains. So let's see what happens here. So here, let's say I start here, I start with the point 1, and then I go to the next set, and I need a metric pair. The metric pair is, of course, again 1. Yes, so the metric chain goes like this, and then always stay at 1, and here it always stays at 0. So this means that for this particular example, we have only 2 metric chains, constant 1 and constant 0, and then when I take the average of each of them, then I get the point 1 here and the point 0 here. And so we are there where we want it to be. The average is now the set itself. Of course, it's more complicated in that example. Here the images are convex, so it will not change the linear combination, but I just want to show you how metric chains are built. If I take a point here, then the metric chain will be just a constant, going like this. But for example, if I take a point here and start to build a metric chain, then I will go to this point first, right? This point, and then from here it will continue. But it's not that I always go from the beginning to the end. The metric pair works in both sense. This means that I can also start with the point here, say, and again build the metric chain, then I go here, and here, and there I have choices. So I can go like this, but I can go also again here, or maybe somewhere in the middle, and so on. So these are the metric chains, the remaining. But the idea is exactly that we always stay at the points that are close to each other. We cannot jump. And that's why this linear combination doesn't possess this convexification property anymore. It's more suitable for working with non-compact sets. Unfortunately, this is a small drawback in this situation. The metric linear combination depends on the order of sets. Yeah, because we always take metric points of 2 neighboring sets. So the order is important. Okay, a little bit about the regularity of the functions we are going to approximate. As I told you, we work with the compact sets with the Hausdor distance, and this is just metric space, complete metric space, so the definitions are exactly the same as usual in any metric space. Yeah, there is nothing new, but just to repeat, we say that a function f is Lipschitz with a constant L if this usual Lipschitz continuity property is fulfilled, and we also consider functions of bounded variation. The variation is defined as usual, as always in the metric space. So we take partition of the interval, and this sum always have a Hausdor distance here. This is the variation on the concrete partition, and the total variation is the supremum of variations over all possible partitions. And we consider the class of functions, set-valued functions of bounded variation. The graph of a set-valued function, again, this is the usual definition, is in this sense is a subset of r to the power d plus 1 dimension more Okay, and it's easy to see that if f is a bounded variation, then the graph of f is a bounded set. We want more. In our setup, we also want that the graph is closed. So we consider the class of set-valued functions with closed graph and bounded variations. And in this case, since the graph is bounded sets, actually I could have written here with compact graph, at least in the final interval. So it's a little bit more here, closed graph, a little bit more. Okay, so this is the class of functions, the basic class of the functions we work with. We want to integrate set-valued functions. Again, here, there is known integral for set-valued functions. This is the so-called Aumann integral. Maybe again I'll show the next. For a set-valued function, maybe I can remove this here. For a set-valued function, I bring here a function whose images are intervals. Images are in R. Let's say this is A, B, and this is the graph of my function, something like this. Yeah. Let's say here's a hole inside. What is the integral? First of all, any function, any single-valued function with the property which is written here as of x, as an element of f of x, is called a selection. So, for example, something like this would be a selection. So this is, for example, a selection. Okay. And the Aumann integral is built the following way. We consider all possible integral selections of our functions and calculate the usual integral, Lebesgue integral, Riemann, and then the set of all possible values of all possible integrals of selections is the Aumann integral. I would say this is a very natural definition. And it is fine when we work with functions with convex images. It is a well-known fact that the Aumann integral is convex and compact if f is a function with our class, a closed image, bounded variation, it exists. But then we again have the effect of the convexification. This means that even if our original function was not convex, the result is always convex. We again consider this same example. So I adopt this example. I consider the function f of x with the constant value. The value is the set 0, 1 for all x in the interval, let's say for simplicity 0, 1. So the graph of this function is 0, 1. The graph of this function consists of these two lines. So now let's see what the integral of this set function is. I need to consider all possible selections. Let's consider the selections of the following type. I take a point alpha here, and I take a selection which is 1 here and which is 0 here, and then the interval is alpha. And you see we obtain each point between 0 and 1 in this way. And it's of course easy to see that it cannot be more than the interval 0, 1, yeah, because all possible selections lay between 0, 1, yeah? So what we see here is the Aumann integral of this function is the complete integral 0, 1. So again, what we obtained is the convex rule. Also here, it doesn't matter if I have a hole here or not, because my selections, they can jump over the hole here, they can fill the hole. So it doesn't matter if I here integrate the function with a hole or without a hole, the result will be the same. And as I told you, this is very good. Everything is quite good when we work with convex functions with convex images, but we don't want to fill the holes. The idea is exactly the same. We take in the Aumann integral, we take too many selections. So we don't want to consider all possible selections, we want to consider selections that are minimal in a certain sense. So we want to follow the same idea. So if, for example, in this example, I only want to have two selections. This is the constant 1 and the constant 0, and then the integral will be exactly the same. Yeah, exactly 0 and 1. And again, the idea is based on the metric pairs. Oh, it's probably not so easy to understand it in a moment, but I will try to explain you it informally. We consider the so-called metric selections. The metric selections are defined in the following way. These are limits, pointwise limits of functions that interpolate metric chains. So we take a partition. For example, here in this example, we take a partition. And then we connect metric chains within a partition. And of course, the result is not necessarily a selection, because you don't know what happens in between. But then we go with the measure of the partition to 0 and consider pointwise limits of all such functions. And these limits are called metric selections. So these are some kind of minimal selections. For that example, what I showed here, let's see what metric selections are possible. So if I start somewhere here, then metric selection going here will be just a constant. It becomes interesting when you go to the boundary of the set. Let's say what happens if it meets the hole. Now, for example, something like this. It meets the hole here, and then it goes around the hole. And since I can go in two directions, for example, I can leave the hole here and stay at the constant. So roughly speaking, the metric selection is a function that tries to be constant when it's possible, and when it's not possible, then it's making a very small differences. We just proved that the set of metric selections has also a nice property that the pointwise limit of metric selections is also a metric selection. Okay, so this is what I told you, that the metric selection is constant in any open interval where the graph of S stays in the interior of graph. And for good functions, for our functions with the closed graph and the bounded variation, it can be shown that through each point there is a metric selection going through it, and the graph of the graph of F is actually a union of graphs of all metric selections. And this is, for example, this is an easy property of the construction, but this is what is a principal difference. The variation, the total variation of any metric selection is bounded by the total variation of the function. And if the function goes from the Lipschitz class, then also the metric selection is of the same Lipschitz class. This means that this violet function, what I showed here, is not allowed. Yeah? It made too many jumps up and down. We can really control how much the variation of the resulting function is. And based on these metric selections, Nira, Elsa, and Elena Mokhov introduced the so-called metric integral in the following way. Okay, maybe you don't see the metric selections yet, they will come. So first, the definition is the following. First, we build for a given partition a metric Riemann sum, which is built in the usual way, like the Riemann sum with the differences. Here we have a metric linear combination. And then if such sums have a limit, when the mesh of the partition goes to 0, then this existing limit is called the metric integral. Here we work with the upper Kuratowski limit, yeah, because we want it to exist the lower Kuratowski limit or the Kuratowski limit will be too much. We cannot guarantee existence there. Or I would say we are not 100% sure about it here, but the upper Kuratowski limit always exists, so we always get the result. The set is not empty if F has a bounded range. And here is a very important result. The definition before it was more or less independent on the class, but here if we really restrict our attention to the class of functions of bounded variation with closed graph, then we can show that the metric integral is nothing else than the collection of integrals of metric selections. So it is indeed comparable in the sense the idea is comparable with the Aumann integral, with the difference that we now integrate over all metric selections. We don't take all positive symmetric selections, but we take only metric selections. Okay, now I think that this was the long introduction as I promised, and now I'm maybe shortly telling you about the content of a particular paper by the 4 authors, which was published the year is 2019. Printed there, actually we wrote it a year ago. For example, the classical Bernstein operator can be written as a metric Bernstein operator for set-valued functions. So this is the usual construction. We take the basis functions, Bernstein basis functions. These are polynomials like here, k is here, 0, 1, 2, and so on. And we take a linear combination of them, and the coefficients of the linear combination are the values of the function at the point k over n. This is just a straightforward generalization of the construction for real valued functions, the well-known construction of Bernstein, where the Bernstein polynomial operator is defined this way. X is here pointed to the interval 0, 1. So as I told you, this is a classical construction going back to Sergei Bernstein. I think, when I'm not mistaken, 1913 or something like this. And he constructed this. This was his attempt to give a constructive, not his attempt, but this was his constructive proof of the Weierstrass approximation theory that for each continuous function on the interval 0, 1, there exists a sequence of polynomials that uniformly converges to F. And this is exactly his construction. So this sequence of polynomials converges to F uniformly on the interval 0, 1, if F is continuous, and you see the construction is absolutely explicit and very, very simple to calculate. So let's do the same for the set-valued function, but here this sum is now the metric sum. Okay, if we work not with the metric sum, but with the Minkowski linear combination, this is what was done by Vitale in his papers. He constructed, he considered this construction, and these are his results about the convergence of F is a function with convex images and continuous on the 0, 1. Then the sequence of this set-valued function converges uniformly to f of x as n goes to infinity. Everything fine, everything like what we want to have for convex images. But if you don't have the convexity, if this is his result also, yeah, if f is just a function with some images, compact images and continuous, then this sequence of b and f uniformly converges to the function which is the following: x maps to the convex hull of f of x. So this is the convergence is uniform in each interval epsilon 1 minus epsilon for any small epsilon. So we have again the convexity equation. So it works for convex images, it doesn't work for non-convex images. The metric Bernstein operator, the result is not necessarily convex, so we can catch more. For continuous set-valued functions, it was studied by Nira Dyn and Farkhi and Mokhov. And the moment I joined the group, we were interested in functions of bounded variation. So we wanted to go away from the continuity, and functions of bounded variations are nice. Actually, maybe I must say that the Bernstein construction, the original Bernstein construction, is not good for functions with discontinuities, meaning discontinuous of second type. Then there are examples where the sequence doesn't converge at all. But if this is a function of bounded variation, then we have jumps only. And then if I take here x being the point of a jump, then it converges to the half sum of the left limit of the right limit. So it's all good. So we wanted somehow to see what happens with set-valued functions when they're just bounded variation. And I just want to show you one example of the function which is of bounded variation but not continuous. This, for example, yeah? So it looks so nice, but it is not continuous. Why? At these both points here and here, we have a discontinuity, we have a jump. Yeah, because the left limit of the function from this side, this is the large interval, and the right limit, this is the union of these two small intervals. This is indeed a jump. So we want to work first, let's say, with examples like this. And this is the result. Don't look too much on the formula, just explain you the ingredients. I have some simpler formula later. So we measure the distance in the following way. For each x, we measure the Hausdor distance between f of x, the original function, and the Bernstein polynomial here. And then we integrate it from 0 to 1. With the continuous functions, we could work with the supremum norm, maximum. Yeah? Since here we cannot, because it will be infinity here. Or maybe not infinity, but what I'm telling, not infinity, of course. It will not converge to 0. This is what I'm trying to say. It will not converge to 0. So when we work with bounded variation, we need to measure distance somehow differently, and we just measure the integral of the Hausdorff distance. Of course, you can play here and put the Hausdorff distance to the power p. Didn't do it, just considered L1 in this sense. And two parameters are playing a role in this estimate: h, some number, and s is natural number. And then there is some estimate. What we see here is the total variation of the function, and here is the constant. The constant is the uniform bound of the function. And now I show you, this was the more exact result. Now I show you a simplified part type of this result. So this integral is bounded from above by the constant, which depends on s. And s, whatever s. Yeah, s is the parameter here. S and the function m and n to some power. So we have here a decay. And since I can take s arbitrarily here, then the limit of this expression when s goes to infinity is -1/2. So in the limit we recover the rate of convergence for the classical Bernstein operator. It is well known that the optimal rate of convergence for the Bernstein is n to the power -1/2 in the real value case. And here we don't have it in this form, but we are arbitrarily close to it. So we have a rate n to the power -1/2 minus epsilon, where epsilon is arbitrary number. Okay, since time is running, I think I have here one more example, but I just skip it. One more example also this type. This was already with these two slides. I thought that probably I won't have time for it anymore. And maybe a last small thing what I'm going to show you between finishing the topic, metric Steklov function. Here I will have estimates with concrete constants. They are based on the L1 norm. This is the metric Steklov mean. So we thought of it as a possibility to smoothen a function. So for example, instead of having this hole with, with really discontinuity with a jump here, maybe we can make something which is smooth, which is Lipschitz continuous, and indeed we can. So the construction is just the straightforward extension of the usual definition of Steklov mean. it can be rewritten for good functions. It can be rewritten as collection of Steklov means or metric selections. And then we have the following properties. The total variation remains. The Steklov mean is a Lipschitz function with the constant, which depends, of course, on delta. Delta is the length of the interval where we integrate. Of course, the smaller delta you take, the worse the result is, the less smooth the result is. Yeah, that's why we divide here by delta when this is smooth. And then finally, the Steklov mean indeed approximate our original function in this sense, and the bound is 2 delta times the total variation of f. Okay, this is now probably not really impressive yet, because this is just the beginning of work with these concepts, and we have more plans using these two techniques, what I showed you, the metric integral and the metric linear combination. We hope that we will be able to extend many classical approximation methods to set-valued functions, and especially for set-valued functions that are not necessarily having convex images. This is, as I told you in the beginning, this is the problem. This is the situation where the usual methods, Minkowski, linear combinations, Aumann integral, do not work. And I already showed you the Bernstein operator, and of course you can think of this whole collection of Bernstein type operators that are designed for integrable functions like Kantorovich, Bernstein, Durkheim, and so on. Another very interesting direction is Fourier analysis. We just spent 2 weeks in Oberwolfach and worked on it. But I think it's too early to claim anything, so we decided we just first want to write our proofs and clean them and really finish all the steps before we announce any results. But this is, I think, a very, very interesting direction. And basically anything what we could do using integral for regular functions maybe can be, through this technique, extended to set-valued functions, so it can be checked. So I see lots of interesting work in the future. Thank you very much for your attention.
Okay, any questions?
So for the Fourier analysis, how do you actually define?
Through the integral with the kernel, with the delta m.
And the Dirichlet kernel you consider?
Real value. Real value. So you have the Dirichlet kernel here, which is whatever. Okay, am I right? Is 1/2 here,
yeah.
And then we integrate with this convolution.
And the integral you understand? Yes.
In this sense, yes. The integral is understood in this sense. We had to extend the notation of the metric integral because we put the weight here. This is so the first part of this. Yes.
Any other questions? Yeah.
Yes.
Do you have any Plum-Leibniz formula for metric integral?
We don't have a derivative.
It's a question.
No.
Strange.
They're also working in the other direction. So I now came to the team to go away from continuity, but three of them, they work further, so they try to understand what the smooth set-valued functions would be and how to work with it. So maybe there will be something coming out. Yes.
Any other remarks?
Лена, а селекция может быть неизмеримой?
The question is whether it's
Well,
The set value
yes.
function could be not measurable.
Well, for the general selection, of course, you can take anything. Yeah? You can take a very bad for metric selection. I think it is measurable. It is very nice, actually.
Well, I mean, you restrict yourself to the measurable.
Yeah. So is your question, so вы спрашиваете, что metric selection автоматически измеримая, да? Или как?
Ну,
It is of bounded variation. So it is, well, I mean, we consider in this entire stuff, we consider functions of bounded variation. This is of bounded variation, I showed it. So any metric selection is of bounded variation. This means this is the difference of two monotone functions. Monotone functions are measurable, so of course it is measurable. So basically, each function of bounded variation is measurable.
But I had a question so regarding the smoothness. Yeah, so you're saying that it's not possible, you don't know how to move from, I don't know, continuity or whatever Lipschitz to the differentiability. Yeah, so is it not clear? I mean, can we consider differentiable set value functions?
Trying, yeah? So to say we work in both directions, yeah? Going away from continuity to the integral functions, but also going, so to say, down to the smaller classes. Yes? So it's in progress. I'm afraid to tell anything concrete now. Just afraid to tell something which wouldn't be correct. It's not so obvious. It's not so obvious, everything.
Yeah, it's not obvious, so I have no just intuition and whatever it
Mhm.
is.
That's the problem. That's the problem. The things are not obvious. Also, my intuition originally was close to zero. The longer I work with the stuff, the better the intuition works.
No, but it's part of
Of course.
Is it possible? There is no negative result such that there is no differentiable set valued functions.
No. So basically, what the ladies are trying to do, they try now to consider first of all differences, just dividing differences.
But basically, you measure the distance between in the images f of x minus f of y, so this is the Hausdor distance.
Yes.
Right?
Yes.
So there is no any statements about that this Hausdor distance has just a limited decay.
I don't know, since I never looked at that direction myself. I would expect that there may be different ways to approach. Probably depending on what you're doing, what you want to do, you can understand it this way or that way. But I don't know.
But some simple sets, say we take the interval and the image is a unit disk. Yeah, we take
Mhm.
the interval and the image is the unit disk. Yeah. Will this set value function be differentiable?
Yeah, in which sense? This is
Yeah.
very, so it's yeah. You need to define the definition of differentiability that makes sense. Exactly. Yes. So work to be done.
Yeah.
Yes.
Okay. Another question. So if not, we.
Thank you.